All right, dude, we are live. What's up, guys? This is Dem Keys, and today we are gonna be. Oh God, chill out. Chill out. Why did you directly unmute? Let's not do that. Okay, all right. Um, let's restart that intro. What's up, guys? This is Dem Keys. Fuck me, dude. What's up, guys? This is Dem Keys, and today we are gonna be getting back to deep learning. Um, I was planning on getting back to deep learning anyways. It was just a matter of, when I would um, when my mind would be diverted towards that direction again. Um, hold on. Just a second here. Where exactly is this being shown? Um, oh, this is why. There we go. I was wondering why Gemini was not being shown, but yeah, here it is. Okay, so today we are gonna be getting back to deep learning. So I was planning on getting back to deep learning eventually, but through Kaggle, through the Kaggle Learn course, because that eventually does introduce you to deep learning, be it albeit through TensorFlow. I was planning on doing it through PyTorch. Um, However, well, my latest distraction, quote unquote, has brought me back to deep learning. So yesterday I was doing research on the Burn framework. Burn is a pure, well, okay, I don't know if I should say pure Rust. I think it's pure Rust. I think, yeah. I think it counts as pure Rust. I stopped for a second there because I was like, it does support multiple backends, though it's supporting different types of backends doesn't mean it's not pure Rust. I'm gonna stay away from the term pure Rust. Um, it's a Rust deep learning framework. Burn is a Burn is a Rust deep learning framework. For some reason, that is not easy to say. Um, uh, so I was doing research on it yesterday, and in the past, I've done research on both Burn and Candle. I don't remember what my reasoning was for deciding to not go with Burn. I don't remember if there was something that I wasn't too sure about with Burn, or if I just had other stuff going on at the time, because of which I was like, okay, at some point later I might visit Burn. I think it might have been that I looked into Candle a little more than Burn. And later on, when I looked at Candle's documentation, the docs themselves were kind of incomplete, and so I didn't really go too far with Candle either. That's not to say that Candle is not a usable framework. There's tons of progress being done in it, and there's a bunch of different features in it. It's just that in terms of using it as a deep learning framework for building and training neural networks, I wasn't able to get too far in terms of the documentation, or I should say that the documentation was kind of incomplete there. So I kind of um, kept it on the side. And I still cannot remember exactly what it was with Burn that I didn't understand at the time. I think it might have been that maybe I was looking at Burn for embedded deep learning. I can't remember what my reasoning was. But yesterday I looked into Burn again, and this time I actually saw a lot of stuff that I liked. I think this time when I looked at it, I understood more of what I was looking at. I think that's another important part of it. I understood what I was looking at, and it seemed really useful. There's a couple of things in Burn that seemed incredibly useful for me. For one thing, there's this whole wait, just a second. Hold on, I need to open up my stream manager and open my stream in the stream manager and load up my chat. Yeah, okay. What was I saying? So something that really that seems really useful for me with Burn is that Burn supports multiple backends, meaning you can write the same Rust code and it would then work on multiple different through these multiple different backends. You can actually support various other platforms as well. So you can use the same code um, for running inference on the CPU, or if you want, you can run it on the GPU. And the GPU part is also very interesting. I'll get to that. I'll get to that in a bit. You can run it on the CPU or on the GPU, and that's for PC based stuff. If you're planning on doing embedded stuff, that is also possible by targeting the ND Array backend, because ND Array supports no STD, at least as far as I know. And through that, you are able to um, write you're able to write code that would be able to execute on these backends. So I don't know about training, but at the very least, inference can be done on embedded framework, on embedded hardware, embedded devices. And again, it's the same Rust code that you have to write, which can then target multiple different platforms. Now, something really interesting about the GPU part is, okay, so in PyTorch, when you are writing your code, you specify a device. The device by default is CPU, but you can specify one of the GPU backends. It can be CUDA, it can be ROCm. I think there's something for MIPS. I'm not sure. And I believe they're adding something for Intel GPUs as well, the newer Intel GPUs. And this is great, right? But Burn uses WebGPU, which handles all of the complexities of writing for different platforms. So Burn can actually then Burn or WebGPU. I believe it might be WebGPU that's doing it. Internally, they have their way of generating the compute shaders that are going to be doing these calculations for you, but they are able to use your GPU if it is available. Not only that, they are also able to use, and I just found this out yesterday, that apparently the integrated GPUs in your CPU can also be used, at least up to like a certain generation, not going all the way back to dual core CPUs and stuff. In the Core I processor family, I think Gemini was saying anything after fifth generation, so like, or anything after sixth, so like seventh, eighth, ninth, and higher generation, you start getting more and more support. If you're talking about like 11th or 12th generation, there's definitely full support for it. So you can actually run compute shaders on that GPU. And you don't have to worry about that. That's the amazing thing. Like, you don't have to worry about writing these compute shaders. All of this is being handled by Burn and WebGPU. And that was really interesting to me. Like, I'm excited to explore this framework because it really seems like if I want to write something that's gonna take full advantage of all of the hardware resources available on the machine, then it makes sense to write it in just a second. Yeah, then it makes sense to write it in Burn, because Burn has its own ways of optimizing things and making them run faster. There's also this interesting tool called, or crate, I guess, called Burn Import, which which can be used to generate native Burn code out of an Onyx model. So if you have, let's say, a PyTorch model exported to Onyx, you can then use burn import to convert that Onyx model, that model that's in Onyx format currently. You can use burn import to convert that model into pure Rust code. So burn import is actually gonna generate the code for you, where you are doing the whole like the whole defining of the network. It'll basically generate the entire architecture for you in pure Rust. So you don't even need to redefine the model. There is a sort of caveat to that. Burn import doesn't support all Onyx operations. There are definitely operations that are not supported. So it really depends on the complexity of your model and what kinds of operations or operators rather, um, what kinds of operators are being used within your Onyx graph. Like for example, I was planning on trying to convert Kokoro TTS to native Burn Rust code, right? But then something like Kokoro TTS, it's a very complex model. It's not a simple like feed forward neural network or a simple convolutional neural network. It's got like a bunch of different architectures that make up that one architecture. So while it can be exported to Onyx, what kinds of operators are going to be used in Onyx, I can't tell for sure, or rather, whether the operators that are used in the Onyx format, whether they're going to be supported by burn import, that is not a sure thing. Fortunately, they do have a list of the operators that are supported by burn import, and I'm sure they're working on adding more. They're working on adding support for more operators over time. Anyways, I'm really interested in burn. I What I decided to do is I decided to learn, because like the first thing to do is actually learn these architectures, learn about these, how these architectures work and how to build. What am I trying to say? How to build neural networks of these architecture of these architectures. More importantly, it's important to learn how the various blocks that build up these architectures actually work. So like for example, in the case of a feed-forward neural network, it would be the building blocks. In this case, would be the linear layer and your ReLU function, which is a nonlinear activation function, and I think there's one more. I don't remember. There was something more in there, but yeah, that's like one of the. These are some of the building blocks of a feed-forward neural network. Convolutional neural networks have their own building blocks. Recurrent neural networks have their own building blocks. Transformer-based neural networks have their own building blocks. Um, so I need to learn about these architectures and how to construct neural networks that follow these architectures. That's the first step. And I feel like learning that through PyTorch is going to be a lot easier than learning it through Burn, because in Burn, I'm going to be focusing on two things. One is actually, you know, implementing the architecture itself. And the second is trying to implement the architecture using Burn's API, which I'm not used to at all. Python's API is like, it's going to be much more straightforward. Once I know what the architecture is, once I know what I'm building, that's the important thing to keep in mind here. I don't know what I'm building right now, or rather, I don't know how to build what I'm trying to build. Right. So I need to first learn how to build these neural networks, and PyTorch, because of its very concise syntax and the very I don't know if I should call it simple API. It's not exactly simple, but it's definitely going to be a lot simpler than the Burn API of PyTorch, I should say. I don't know if I mentioned that I was talking about PyTorch before when I was talking about the API thing, but yeah, my point is, I feel like because like I have learned how to build feed forward neural networks in PyTorch, so I can say that the syntax is relatively simple, which is a good thing because it's not as verbose. It's not nearly as, it's still pretty verbose, but it's not nearly as verbose as um, I'm losing my words. It's not nearly as verbose as if I were trying to do it in Rust. In Python, the syntax is much more concise. The API for PyTorch is also pretty concise, and that exact same thing, if I bring it to Rust, it's going to be incredibly verbose. So I'm gonna have two challenges there. One is actually learning about the architecture itself, and the second is learning about Burns API and how to use that API to build this architecture. So for the time being, I want to focus on just learning about the architecture, and once I actually know about the architecture, then we can move on to um, trying to build it using Burn, because I do have ideas that I very much would like to execute. Some of them are for embedded devices, which I'm really excited about. That's another reason why I want to look into Burn, because eventually once I start doing, once I continue, I should say, my ESP32 coding stuff, I would like to, introduce deep learning into it. Okay, so what do I have planned for today? The first thing we need to do is, um, so I think I'm on the wrong thing right now. I shouldn't be here. Give me a second. Right. So wait, are we good with the, okay, nope, we're not. So this thing is a bit stuck. I need to, okay, it's not stuck anymore. So I need to remove this. This was just as an example. Here, actually, okay, I need the Gemini. Yeah, let's go back and let's do, um, what was it? Learning DL. Oh, what just happened? Oh, okay, no problem. Okay, so we are in here. Here I need to fire up Gemini. I don't need Gemini in this, so I can quit this. Right, so Gemini is started up here. Here I'm gonna prepare the entire. Actually, yeah, I need to write down the the prompt, because I'm gonna prepare a prompt that Gemini is gonna then follow. Just a second. Okay. So I can quit this, and I do have. Okay, okay. Yeah, so here I need to create a new environment. We first thing we need to do is install PyTorch. I believe, yeah, okay. I can install it using using UV. UV is, by the way, for anyone who doesn't know, UV is a Rust-based Python package manager and also project manager. So you can use it for multiple purposes, including initializing and what was the next word I was going to use? Initializing and managing, I guess, projects. Like I'm talking about one level above just Python environments. Like you can, this dude, I looked into this. It became a bit of a headache for me eventually, initially, because I didn't fully understand the difference um, between how UV was doing package management versus how UV pip would be doing package management, because UV does have its own version of pip which you can use to install your packages. And if you are going for a project that is where you just want to be able to install packages without any any very strong rules for package versions and dependencies and stuff like that, you definitely want to go with just pip. But in situations where you absolutely need to be able to reproduce the results, and because of that you need all the versions of all the packages to be fixed, and you don't want versions getting changed here and there, to the point that you actually need like a toml file to describe all of the dependencies and their versions and all of that stuff, then you want to use UV's project management feature. You will come across a lot of Python projects where in the repo you'll find a uv.lock file, and I think there was another file as well. I forgot what that was. I think that was like a project toml file. Usually, I believe it's the UV lock file that you have to use. You just clone this repo, and then you run UV sync, and then UV is going to take care of all of the dependency management for you based on the information that's within these files. I forgot exactly which one it reads from. I believe it reads from UV lock, but there is information in the other file as well. I forgot exactly what that other file was even called. Maybe it's the pyproject.toml file. I don't remember exactly, but you do specify dependencies there as well. But yeah, if you want absolutely reproducible results, then you definitely want to go with a much more stricter version management system. And the project management side of UV helps you do that. But if you just want to be able to install packages real quick, then UV pip is the way to go. And holy shit, it is so fast. Like, I'm not even kidding about that. It is crazy fast. So we're gonna do with, okay. What does PyTorch say? It says it requires 3.1. I'm trying to decide if I want to do 3.13 or 3.14. I don't remember if I have 3.14 installed, so I think I'll go with 1.3. So that's our environment. Then we activate the environment, and then bin activate, then UV pip, and here we need to specify, wait, I don't remember if this accepts the index URL option, or what is like the way to do index URL here. Use UV help pip for more details. Okay. UV help pip. Okay, okay. There was a certain option. I mean, this would be a lot simpler if I just installed it using... Wait, can I just use regular pip flags? Because these flags that are mentioned here are for pip 3. They are not for UV pip. Also, I'm not trying to install the CUDA version. I need to keep that in mind. Oh, you know what? You know what? That simplifies things. If I'm just doing the CPU version and not doing CUDA, I don't have to specify an index URL. That simplifies things for me. Okay, UV pip install torch and torch vision. Okay, so now it's going to download the whole thing. You can see all of the downloads taking place. Wait, I'm just making sure that I got the right... Oh, hold on. We need to stop the install. I made a mistake here. So I'm just gonna deactivate because... Hold on, I'll talk about it in a bit. Let's delete this and let's create the new environment, then activate again. We do need to use the index URL flag. Let me just look it up here. UV pip. Can you not write pop? Okay, index URL. Okay, pip style index URL, so and so package indexes. Okay, hold on. I'm looking this up on another machine. Defining an index. Okay, this is in pyproject.toml. That's not what I'm looking for. How do I just do the simple pip install method? Give me a second. Right. Installing and managing packages. Okay, okay. Install so and so, so and so. Install from GitHub. Editable packages. Install from package file. Install package from files. Where is the index option? Because this specifies the primary package index URL, and this specifies additional package index URL. You know what? We're just gonna go with the regular way of doing it and see if it works. So UV pip install torch vision, and then we do index. What did I just do? Index. Index URL HTTPS download.pytorch.org. What is going on with my typing, dude? Holy shit. Slash, I believe that's wheel, and then CPU. Let's see if this works. I believe it worked. Yeah, I think so. I think it worked. So this is just downloading PyTorch now. give it a second while it finishes this download. And fortunately, because this is a CPU thing, I believe that means that it's not going to be, oh, look at that. Look at that. So the entire installation was done within like, I don't know, less than a minute. That is insane. That is insane, dude. Another thing I need to see is, well, I don't think this is going to be too much of an issue, but yeah, let me see what the situation is. Because like when I try to open up, even with like something like Burn, I opened it up in NeoVim. I created a project, added Burn as a dependency. I ran cargo build, and then I opened up NeoVim. I opened up the project in NeoVim, and Rust Analyzer took a good like five, I believe it was five, around 5 GB. Basically, we are back to the same issue that I was having with what is it? Bevy. And when I tried to run the linker, I think it went up to like maybe 1.5 GB. When I tried to do cargo run and it had to, go through the linking process, that took like 1.5 GB. I have to look into ways to minimize the memory usage in those situations. To be fair, well, I was about to say, to be fair, I might have imported or I might have added the crate with like all of the features by default, but I think I did specify one feature, which was web GPU, and that's about it. So it by default it enabled STD, which is the standard feature, as in it's going to be using standard library related stuff and not no STD. And then there was another feature that I don't remember the name of, and then there was web GPU. So I think that might have been like the bare bones installation. I'm not sure. Either way, yeah. Fortunately, I do have a machine where I can spare RAM to do this kind of development. Though this does mean that if I'm creating something that's going to be training a neural network, I can't have the code and the binary open at the same time. So I'm going to have to close NeoVim whenever it's time to train a neural network using the binary that I'm making. I'll have to close NeoVim and then run the training elsewhere. Which, okay, I do have another laptop. This is actually my mom's old laptop because she got a new laptop. And so I took that old one. That the old one's hard drive was failing. And so things have been running really slow with it. Other than the failing hard drive, it seems like a lot of other stuff is just it's fine. Like there's no issue with a lot of the other stuff. And so where was I going with this? Yeah, the hard drive is failing. Other than the hard drive, all of the other stuff seems fine. The other hardware, the RAM, the CPU, and all of the other components and stuff, they seem to be working pretty well. So I was thinking, what if I was able to run an OS on this machine without actually having to install the OS? I was wondering if there is such a thing. It turns out PXE boot is how you do that. PXE boot is how you would go about accomplishing this. Through that, you can actually you can launch the operating system on this machine. You can power up this machine and launch the operating system on this machine, but from another machine. So you would be controlling it from another machine. The OS would be transferred to this machine and launched and run on this machine. and then once it's running, you would receive the output of whatever is being run. And in situations where a hard drive is needed for certain purposes, you would use I forgot what it's called. It's a kind of network access storage, but it's not exactly that. It's it's built specifically for this purpose. It's optimized to be used in these kinds of situations, and it's basically a hard drive being accessed over the network. So the machine that you use to launch the OS into this what we're going to call a compute node, from that host machine. On that host machine, you're going to have a certain amount of hard disk space allocated to serve as a quote unquote hard drive. So that's an interesting it's an interesting setup that I'm very interested in checking out, because that's one of the few ways that I'm going to be able to use this laptop's hardware, not hard drive. That's one of the few ways that I'm going to be able to use this laptop's resources. And if I succeed in it, I will essentially have an extra compute node. Actually, my first compute node. I'll have my first compute node that is just ready to do whatever computations I need. And one of those computations, or one of those kinds of computations, would be running one of the TTS worker nodes on it. So that's something I'm excited to look into. I haven't gotten the chance to look into it yet. I do need to set up the software on the host computer, and then I need to connect this laptop to my router using Ethernet, because it's not running off of Wi-Fi. The entire thing is meant to be like a wired connection, which also, thanks to certain people on TikTok, I was able to sort of get the idea. Basically, I got it from them. Uh, to use multiple Raspberry Pis as sort of a cluster, but as one like big server setup. And within that server, because you have these multiple Raspberry Pis, these are multiple nodes in which you can run one or more processes or entire OSs if you want. But you can also run multiple containerized processes, which are running like directly on the kernel. They're running on a layer that is running on the kernel, but they're not running on an OS. That's the point. It's interesting, dude. Like, holy shit. There's, thanks to, again, people on TikTok, people who have been showing off their home lab setup. I got this idea that, hey, if I can get a Raspberry Pi, I actually do have a Raspberry Pi, but I have an old one. I have a Raspberry Pi 3 Model B. It should still be usable, but yeah, if I get one of the newer ones, apparently the newer ones, they come with PXE boot enabled by default, so I won't need to do any sort of configuration in it. Something that I was trying to do in the Raspberry Pi's case is avoid having to install anything onto a SD card. Man, we're supposed to be doing this PyTorch stuff, but I've been sitting and talking about the home lab setup thing. But dude, I definitely, holy shit. If I could, first of all, get my hands on some money, um, but then also manage to get a Raspberry Pi delivered to where I live. I want to get it like directly from the source. But I'm saying source. I want to get it directly from like um, the dealer. I don't wanna order it off of, because like I can order cheap knockoff versions off of like AliExpress or even Amazon or something. And if it were all that cheap, like if I can manage to get it super cheap, then I would do that. But it's not all that cheap. Like if the price difference was, massive, and I was saving a lot of money by going for the knockoff thing, I would have done that. But if I pay a little bit extra, then I can get it from Raspberry Pi directly, and there's like proper software support and all of that stuff. With the knockoff stuff, You have to rely on open source software, and the support for different hardware is kind of iffy. It's not always like a sure thing. Though I could do more research into it and see if I can manage to do something. But for now, hardware that I do have, I mean, I have that Raspberry Pi. I still have to like do the configuration on that for PXE boot. Once I manage to do the PXE boot configuration there, I'll have yet another compute node. But for now, this laptop, I want to turn this laptop into a compute node. I wanna see what that setup is like. Give me a second here. And this should be exciting, dude. This should be interesting once I've set the thing up. Anyways, so we're supposed to be doing PyTorch stuff. Okay, what else was I supposed to do here? So okay, this installed NumPy. I don't see pandas. I do want pandas. I also want matplotlib. I don't think I need scikit-learn in this. Um, for installing data sets, I think I could just use the data sets that are provided by PyTorch for now. However, I was tempted to also look into the Hugging Face datasets library because there's a lot of datasets hosted on Hugging Face, and the datasets library makes it easy for you to uh, download and use these datasets. Apparently, their API is also incredibly simple. It's like one or two lines to immediately download a dataset based on whatever um, account name slash dataset name that you give. Let me just look at the tutorials here. Okay, quick start, audio, vision, NLP. Um, Start by installing datasets. Oh, you know what? Okay, let me do it here so then I can decide if I want to, because that's gonna dictate. Because I don't know if I mentioned this at the beginning of the stream. What I was gonna do is I was gonna set up um, a prompt in Gemini, and I was gonna tell Gemini to generate the entire syllabus for me, and then we're gonna go step by step in that syllabus. Give me a second here. I'm just opening something up. Okay, these are the docs. You did not have to scroll down. Let's scroll back up. All right, here we are. So this is the datasets library. So datasets is a library for easily accessing and sharing AI datasets for audio, computer vision, and NLP. Okay, load a dataset in a single line of code and use our powerful data processing and streaming methods to quickly get your dataset ready for training in a deep learning model. Backed by the Apache Arrow format, process large datasets with zero copy reads without any memory constraints for optimal speed and efficiency. We also f- we also feature a deep learning. We also feature a deep integration with the Hugging Face Hub, allowing you to easily load and share a dataset with the wider machine learning community. Okay, tutorials, quick start. All right, let's zoom in here so I can see better. All right, check out chapter 5 of the Hugging Face course to learn more. Wait, there's a complete Hugging Face course? Like I'd seen a Hugging Face Transformers course, This is an LLM course. I think I have this in my list. I was planning on looking into, um, yeah, this is the LLM course documentation. So let's take a look at the introduction here. Because I believe I had looked into this when I was trying to decide between the LLM course and the Hugging Face, the small course, I think it was called. Okay, welcome to the Hugging Face course. This introduction will guide you through setting up a working environment. If you're just starting the course, we recommend you first take a look at chapter 1, then come back and set up your environment so you can try the code yourself. All the libraries that we'll be using in this course are available as Python packages. So here we'll show you how to set up a Python environment and install the specific libraries you need. We'll cover two ways of setting up your working environment using a Collab notebook or a Python virtual environment. Feel free to choose the one that resonates with you the most. For beginners, we strongly recommend that you get started by using a Collab notebook. Note that we will not be covering the windowing system. Window, the Windows system. Okay. Uh, we will not be covering the Windows system. If you're running on Windows, we recommend following along using a Collab notebook. If you're using a Linux distribution or Mac OS, you can either approach what? Oh, you can use either approach described here. Okay. Fortunately, I am using Linux. Right, so you need transformers to be installed, specifically transformers, and I'm not seeing anything else needing to be installed. Yeah, that seems to be it. Okay, this course will teach you about the large language models and natural language processing using. Where did I see the? No, 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 no. This course will teach you about large language models and natural language processing using libraries from the Hugging Face ecosystem like transformers, datasets, tokenizers, and Accelerate, as well as the Hugging Face hub. What does this library do? Accelerate? Give me a second. Let me open this up and look at this. A simple way to launch, train, and use PyTorch models on almost any device and distributed configuration. Automatic mixed precision and easy to configure FSDP and deep speed support. Okay, but how does this make it? Okay, run your raw PyTorch training script on any kind of device, easy to integrate. Accelerate was created for PyTorch users who would like to write the training loop of PyTorch models, but are reluctant to write and maintain the boilerplate code needed to use multi. Oh, okay, like that. Okay, it provides like an abstraction layer. Yeah, it mentions here Accelerate abstracts exactly and only the boilerplate code related to multi GPUs, TPUs, FP16, and leaves the rest of your code unchanged. Here's an example. Accelerate abstracts exactly and on. Oh, I read that already. Oh, so it's like modifying your code. It's going to study your entire code and then modify it to run easily. Okay, that's convenient, dude. Yeah, yeah, that's convenient. That is useful. Okay, coming back here. Uh yeah, dude, I can't remember what the hold on. I think I had the course names somewhere here maybe. Yeah, there it is. Hugging Face LLM course. I already have this in the list, and I believe I added this to the list because of all of these. So like it kind of covers a bunch of different things in the Hugging Face ecosystem. So by the time I finish this course, I will have learned a decent bit about the Hugging Face ecosystem, and I will have also um, learned how to use these libraries. And there's also the 5-day Gen AI course, and there's a 5-day AI agents course. This it was 5-day AI agents, not just 5-day agents. AI agents. We were supposed to do that, dude. I started that and then I just never went back to it. But I do want to go back to it because okay, one of the reasons I it's not that I abandoned it. It's just that I remember as we were doing research on that, at some point I was wondering, hey, um, is is the concept of AI agents a thing in the Rust ecosystem? Let me look it up. And then I looked it up and then I found auto agents. And then I found out that auto agents is based on, is built upon Ractor. And then I started doing research on Ractor. That told me that, okay, this is an actor framework. And then I started looking into actor frameworks, exactly what they are. I got interested in that concept because I learned that, okay, I can apply this concept to other situations, not just specifically to AI agents. There are other situations where I can apply the concept of an actor. And then I started learning about how Ractor works, which led me to Tokyo. And then I started learning about how Tokyo works. Um, and now here we are. Anyways, so um, we we are gonna. Oh, I need to install. Yeah, so UV pip install. Let's install pandas and matplotlib. Do I also need? No, it's just a simple like in terms of graphs. All I need is a simple line graph. So I don't think I need like Seaborn and stuff. I probably don't even need scikit-learn. Yeah, yeah. Okay. In the meantime, while this is taking its time to do stuff, uh, man, that is some, holy shit, that is some lag. That is insane. Okay. UV pip install pandas. Somehow I only seem to be having this issue with my, when I'm trying to access, um, when I'm trying to do SSH stuff using Wi-Fi. I don't seem to be having this issue on my other machine where it's a wired connection, or at least the lag is significantly less. So much so that it's very unnoticeable. Worst case scenario is like once in a while there's a little hitch, like a 1 second, 2 second kind of hitch. But then on my other laptop where I'm connecting through Wi-Fi, if there is a hitch, it'll be a couple seconds. It won't be just like, 1 or 2 seconds. It'll be more. It'll be 5 to 10 seconds, maybe 15 seconds. Anyways, UV pip install pandas, matplotlib. Did I spell all that right? Yeah. Okay. It's downloading and done. Installed. Okay. Now I guess we can open this up in NeoVim. And let me activate the environment here. Wait, that's odd. Does bin not contain that? Permission denied. Uh, hold up. I don't think deactivate is required here because I did deactivate the environment earlier. Oh, oh shit. It's supposed to be source. Forgot about that. Right, so I can then use this to run the environment. So here we can create a new thing, pio1.py, and open that up and save it. Also, we can come here and, no, you know what? Because of the bit of lag, I think I'm better off typing it elsewhere. So, you are a tutor. You are gonna teach me about feed forward neural networks. We will be using PyTorch as our deep learning framework. Uh, and we will be doing coding in Python. Let's just mention that in case it pulls out something. Well, no, PyTorch is specific to Python because PyTorch provides Python bindings for the Torch library, um, which is written in C, C++. Okay, okay. So we will be doing coding in Python. I want you to create a syllabus for me. See, I want this to be more focused on building the neural network itself and not more focused on learning about the PyTorch API and more about the PyTorch framework. I would like to focus on like feed forward neural networks specifically. We'll be using PyTorch as our deep learning framework. We will be doing coding in Python. I want you to create a syllabus for me. Convert this syllabus to JSON and write it to FCNN syllabus.json, and also, wait, also print out, no, print out this syllabus, hold on, print out this syllabus for me, then convert this syllabus to JSON and write it to FCNN syllabus.json. Okay. Aside from this one write operation, I don't want you to take any other write operations at all. If anything needs to be done, tell me to do it, and I'll do it. This way, I get to learn. Uh, yeah, this way I get to learn. Then what else? Oh, yeah. At the end of each chapter, I would like a small exercise so I can practice what I've learned. Okay, you are a tutor. You're going to teach me about feed-forward neural networks. We'll be using PyTorch as our deep learning framework, and we'll be doing coding in Python. Um, hold on. I have the coding environment set up already. I have created the VN, installed the necessary uh, torch packages, and have activated, well, saying activated is not necessary. I've created the VN, installed the necessary packages. What else was I going to say? Yeah, I think that's it, right? I've created the virtual environment and installed the necessary packages in it. Now, yeah, for the sake of simplicity, actually, I'm wondering if we should revisit the basics of PyTorch again as well, or is the syllabus gonna contain some of the basics? Because the concept of data sets and splitting the data set and stuff like that comes under like a little bit under, because there was a whole thing of, I forgot what it was. Data, I don't know, data set loader, data set something else. There were two separate things. I forgot all of that. It's hold on. Um Wait, do they mention UV here? That this just occurred to me. Okay, package manager, pip, and that's it. I don't think they mention UV. Though, I mean, um, doing it through UV pip wasn't all that different. So, yeah, I mean, I don't think they need to mention. Okay, start locally. Okay, okay, installing. Right, fine, great. Um, okay, let's just go look at the tutorials. Give me a second. Was this the one? I don't think this was. Oh yeah, data sets and data loaders. That's what it was. So you had a datasets class and then you had a data loaders class as well. What I'm wondering is, yeah, you know what? I think because where is it pulling datasets from? I believe it does have like its own. Hold up. Okay, PyTorch domain libraries provide a number of preloaded datasets such as fashion mnest, that's subclass so and so, and implement functions specific to the particular data. They can be used to prototype and benchmark your model. You can find them here: image datasets, text datasets, and audio datasets. Okay, I guess it's going to use the fashion mnest dataset. Okay, right. Is the prompt ready? Is there anything more I need to ask here? Okay, then convert the syllabus to JSON and write it to so and so. Aside from this one write operation, I don't want you to take any other write operations. That sounds like if anything needs to be done. Okay. All right. I think that's I think that's it. Let me just do something here. All right, that should do it then. Yeah, yeah. I think that should be it. Okay. All right. So let's see how this goes. Actually, I might need to give Gemini some. Just a second. I need to. Okay. Create project specific Gemini.md file within it. Oh, I think it's just saying stuff. Right. While Gemini is generating the stuff, I will take a sip of my energy drink and I will hydrate. And yeah, then we'll continue. Okay, so our syllabus is ready here. Let's take a look. Of course, here's a syllabus designed to teach you about feed-forward neural networks using PyTorch. Syllabus: Introduction to Feed-Forward Neural Networks with PyTorch. The building bo- the building blocks, tensors in PyTorch. What is a neural network? A high-level overview, introduction to PyTorch and its core data structure, the tensor. Okay, creating tensors, essential tensor operations, the concept of a computation graph and automatic differentiation. All right, then constructing your first neural network. Okay, right. So here we construct the neural network, instantiate it, and pass a random tensor through it to see the output shape. Um, okay, activation functions, then measuring performance, loss functions, then optimizers, and then we have the full training loop. Okay, cool. Let's get into it. Excellent. We are ready to begin. So let's start with chapter one, the basic building block. No, the building blocks, tensors, and PyTorch. What is a neural network? A high-level overview. At its core, a neural network is a computational model inspired by the human brain. Think of it as a machine that learns to find patterns in data. You know what's funny about this? Well, not about this definition, but about me learning about feed-forward neural networks. This is probably the second or third time that I'm learning about about feed-forward neural networks, and that's not because I haven't understood feed-forward neural networks. I mean, there's still a fair bit of um, understanding that I have to do. There's still a fair bit of learning that I have to do, a fair bit of exploration and experimentation that I have to do with feed-forward neural networks to properly understand exactly what they're doing. But that's like very deep research that I want to do. I very much know the basics of feed-forward neural networks and how they work. What I'm trying to refresh my knowledge on here is how to build it using PyTorch's API. Because I've repeated this thing multiple times at this point, to the point that I know how this works. I can describe it conceptually, how it's working, how it's built, how the training is done, and some of the math behind it. I do need to sort of remind myself of how it was done. More specifically, cross entropy loss. It was really interesting seeing the uh, how the logits that are produced by the network, they get converted into probabilities, um, and then you are able to use that probability as what as basically the neural network's prediction or the neural network's guess in the case of like a classification model. Anyways, let's learn this. This is definitely the first time I'm learning about feed-forward neural networks in PyTorch through Gemini. So far in the past, I've mainly been doing it through the PyTorch website. So this is a this is my new common way of learning about, well, a bunch of different things. Okay, imagine you're trying to predict a house's prices. You have data like its size, number of bedrooms, and location. A neural network takes these inputs, passes them through a series of neurons organized in layers, and produces an output. Hold on, passes them through a series of neurons organized in layers and produces an output, in this case, the predicted price. The quote unquote learning part happens when you show the network many examples of houses with their actual prices. The network makes a prediction, compares it to the real price, and slightly adjusts its internal neurons to make a better prediction next time. This process is repeated thousands of times, and eventually the network gets very good at predicting prices for new unseen houses. That's the basic idea. We give it data, it learns the relationships within that data, and then it can make predictions on new data. Okay, introduction to PyTorch and the tensor. PyTorch is an open source library that helps us build and train these neural networks. The most fundamental thing, the most fundamental building block in PyTorch is the tensor. A tensor is a multidimensional array very similar to NumPy's ND array. It's the primary way to store data and manipulate data in PyTorch. Let's get our hands dirty. The best, the best way to learn is by doing. I'll provide you with the Python code snippets. Please create a new Python file, type, type or paste the code into it, and run it. This will help you get a feel for how PyTorch works. First, you need to import the torch library, then we create our very first tensor. Your turn. Create a file, okay, and add the following code, then run it from your terminal. All right, so we have this here, and then this here. Yeah, we can do chapter 1. We can create a new thing. So let me just save this. I'll use this for some other purpose later. This would be called ch-01.py. Actually, I wonder if I should be doing this on, like, if I should change the windows. Well, okay. Chapter 1. All right, save that, and okay, we can begin. Torch, then my underscore list equals 1, 2, all right, 3, 4. Okay, my tensor equals torch.tensor my list. Then print, yeah, we can do it in this way instead. My first tensor, and then in here we do my underscore tensor. Then tensor shape. Right, tensor shape. My tensor dot shape. Okay, save this and run it. Should I run it here or should I run it here? Well, okay. Python 3.13. Okay, done. Right. Let me know the output once you've run the script. Well, yeah, I could just uh anyways, Done. It outputted the is that the spelling? I don't know. Outputted, whatever. The tensor value and shape. Oh, dude, it also just occurred to me that if I set up this compute node, then in situations where I'm not currently using that hardware, I could actually be hosting some kind of LLM there and running it on that hardware, because that hardware actually has um, it has an okay CPU. It also has a discrete GPU. I believe it has an AMD GPU. I don't remember. But like if I'm running Linux, I should be able to use those. I should be able to use the GPU resources. Okay, right. Moving on. Um, Great. You've successfully created and inspected your first PyTorch tensor. Let's continue by exploring more ways to create tensors and perform some basic operations on them. More ways to create tensors. PyTorch provides many functions to create tensors with initial values. Torch.zeros, torch.ones, torch.rand, rand_n. Rand_n is for, based on normal distribution. Okay. Hold on. No, no, no. It creates a tensor with random numbers from a uniform distribution, and then rand_n creates a tensor with random numbers from a normal distribution. What does a uniform distribution's shape look like? Let me just look that up, because I know that a normal distribution's shape is more or less a bell curve. Um, Uniform distribution. Rather, let me say uniform versus normal distribution. Um, this is kind of confusing because it seems like while a normal distribution is it follows a bell curve sort of thing and it has certain properties, a uniform distribution is sort of similar values. So like, okay, if you go by what this thing is saying here, um, so okay, it says between 0 and 1. Wait, let me see what Gemini is saying about normal versus. Okay, the primary difference is the uniform distribution has equal probability for all outcomes within a specific range, a rectangle shape. Oh, the the values that I was seeing were like binned values. Okay, so it creates bins and it gives probabilities for each of those bins. while the normal distribution has outcomes that are more likely to occur near the mean. Actually, that's a good point as well. If we are visualizing the probability of values occurring, they all have an equal probability. That's what they mean. Okay. So it's not like an integer based thing. It was more about the probabilities of the values occurring. And that kind of makes sense then, right? If you think about it now, like after I don't know how many months after visiting this topic, because I had visited this topic like way back when we were doing Kaggle stuff, before the recent Kaggle thing that I did. I'm talking about like months ago, maybe even a year ago, when we were studying about what do you call it? What do you call it? When we were studying about I'm losing my train of thought. When we were studying about stuff like variance, mean, standard distribution, and a couple of other things, like there were topics surrounding that, stats related topics surrounding that. When we were studying that, that's when I had looked into normal distribution and I was trying to wrap my head around the concept of normal distribution. Um, and I feel like when you it depends on how, like, when you visualize it a certain way, then you're able to make sense out of it. And a normal distribution follows a very specific kind of shape, but it's not just about the shape. That shape, it just so happens that when you look at the mean and the standard variance of, um, no, not standard variance, standard deviation. Did I say standard variance previously? The standard deviation. Yeah, when you look at the mean and the standard deviation of that specific shape, it just so happens to have very specific values, and then that's what gives you a normal distribution. Anyways, okay. Uh, torch.mt creates an uninitialized tensor. The values will be whatever was in memory at that time. Oh, I've never actually done this. So this creates a tensor with garbage values. I'm curious about this. Okay, let's modify our chapter 1 file to include these. Okay, zero tensor. Oh, then we're gonna print all of them out. All right. Okay, let's try that out. You can also specify the data type. Please update your chapter 1 file with this code and run it. Observe the different types of tensors created and their values. All right, let's do that. Okay, so zeros tensor equals torch.tensor. Uh, this needs, hold up. Okay, so here we seem to be giving it a shape. However, oh wait, what did I typed tensor. I wasn't supposed to type tensor. I was supposed to type zeros, torch.zeros. That's why I was wondering why we are specifying a shape here, or in this case, size. Well, here now it's size, but like before it was showing data. So that's why I was confused, but it was because I was doing torch.tensor, not torch.zeros. Okay, then ones tensor equals torch dot ones, and then here it'll also be the size, though here it's not taking a tuple, is it? Here, okay, what's the second thing? Size, a sequence of integers. Oh, a sequence of integers. All right. Okay. Shape can be passed as separate arguments. All right. Can be a variable number of arguments or a collection like a list or tuple. All right. Okay. Then rand tensor equals torch dot rand. This is going to be the size. Okay. All right. Here also. Yeah, whatever. I mean, we can pass in a tuple, right? It accepts a tuple, so we can pass in a tuple. Then rand n underscore tensor equals torch dot rand n, and this also takes a size 1 4. Then empty tensor equals torch dot empty 2 2. Hey there. Sorry, I'm trying to read your name. Deeb. Hey there, Deeb. Welcome to the stream. Hello, hello. How's it going? Thank you for lurking. I am currently learning slash relearning about creating and training and using feed-forward neural networks using the PyTorch framework. What I did is I set up a prompt in Gemini. I told Gemini to create a sort of syllabus for me, and Gemini is then going to teach me how to create and train, how to build, train, and use a feed-forward neural network using PyTorch. This like there's a lot of different subjects that are involved in there. So here's the syllabus that Gemini generated for me. There's 6 chapters here. First, we are looking into tensors. Fortunately, I do already know the basics of PyTorch. So a bunch of these initial things are going to be just sort of refreshing my memory. And the later stuff, I've also looked into feed forward feed feed forward neural networks before, so it'll be kind of refreshing my memory. But this time, I'm learning it through Gemini, and hopefully the learning experience is going to be kind of different. Later on, once I've refreshed my basic knowledge of feed forward neural networks, I would like to go into more complex stuff like understanding how exactly the network is learning and what the network is learning. Because I remember in the past, I kind of got stuck on that topic because I wasn't able to visualize exactly what the neural network is learning. It was more like, okay, it's learning these features, it's learning those features, it's learning the connection between so and so things. But then I wasn't able to visualize that because the learning is being represented in terms of numbers. So I need to find a better way to understand and visualize this. Okay, I'm still at an intermediate level of Python, and this seems like a level I'll be reaching soon. Thank you for explaining that to me, and I would love to body double as you code. Hell yeah, hell yeah. That's pretty awesome uh, that you're doing Python stuff. Feel free to mention like what all are you working on? And yeah, feel free to hang out and lurk as I'm learning stuff. Or like you can also work on your own stuff. Hold up. let me scroll down here. Okay, empty tensor. Okay, what else was there? Yeah, tensors of different types. So float tensor equals torch dot ones. This is the size, and then we specify the type, which would be torch dot float 32. Okay, then int tensor torch dot tensor. Uh, wait, is this the size? This is not the size. This is the these are the values. So you're passing in a list. And then we specify dtype, which is going to be int64. All right, now we need to print all of these out. I don't want to have to type a whole bunch of stuff, so I'm just going to do this. Okay, what was it? Zeros tensor, then ones tensor. Okay, at the moment I'm working on understanding APIs and working within the responses it returns. Hell yeah. Hell yeah, that's pretty awesome. Rand tensor, rand n tensor, float tensor, and int tensor. Okay, we should be good to go. I probably should have... Wait, what happens if I print this out? Oh, um, yeah. Okay, okay. If I would have made them separate statements, hold on. Yeah, okay. If I would have made these separate statements, it would have probably showed the shape of each of them. Yeah, I think so. Because if I'm like just printing one, so like let's try zeros tensor. Which one, which one is the zeros tensor? Oh, the last one. Yeah. Oh, you know what? No, it's not. Okay, I just realized the shape was being shown previously only because I explicitly asked it to print the shape up here. Okay, cool. That's done. Just a minute. We will continue. Wait, please update your chapter 1.py file with this code and run it. Observe the different types of... let me type it here. Done. It printed out. Actually, yeah, I didn't observe all the... Hold on. Yeah, let me just do that. Um, Hopefully this respects new lines. I'm not sure. Let's just hope. Okay, save, come here, run this. Right, 0, 1, then we have our random, then random based on a normal distribution, then... Wait, this is interesting. It's random values creating a normal distribution. I'm curious about this. Wait, uh, let me... where's rand n? This is a normal distribution, right? So it's one row, multiple columns. Let's make it 20 columns. I want to look at the numbers. So these are going into the negatives. Yeah, no. Okay, they're scattered all over the place. I was trying to find a pattern within the array itself, like within the list itself, but no, that's not the case. Okay. Hold on. All right. Okay. Yeah. So done. It printed out all the values. Okay. Now let's see what is next. Excellent. Seeing all those tensor creations is a good step. Now, let's look at how we perform operations with these tensors. PyTorch tensors support a wide range of operations, much like NumPy arrays. Essentially, tensor operations, what? No, essential tensor operations, arithmetic operations, indexing and slicing, and reshaping. Okay, all right. Okay, let's update your chapter 1.py again to demonstrate these. Add the following. I'm assuming it's at the bottom. Yeah, new tensor operations code. Right, so these are tensor operations. We create tensor A, tensor B. Yeah. Um, hold on just a minute. Okay, right, so we create two tensors. Great. I'm wondering if I would have had doubts about this. So hold on. I mean, I'm not new to tensors, but like something that I usually end up having issues visualizing um is multidimensional tensors, like especially once it goes past 2 dimensions. Because like I need to be able to sort of visualize the thing, even if I'm visualizing it in on a two dimensional plane. I need to be able to visualize it, even if it's, as like containers. I need to, and this reminds me, I was going to work on something, and this was like a while back that I was going to work on it. Now, if I do work on it, it's going to be using, it's probably going to be using Nano. I think. I think so. I might use Nano to sort of render an image. I need to see if there's a way to export whatever Nano is currently displaying on screen. If there's a way to export that as, or if there's a way to like create an image data structure and then export that through Rust. There has to be some way. I just need to think about it because like I would need to, you know, create an image data structure kind of thing and then draw on that image data structure. whatever, though, I mean, I wouldn't be drawing on that structure directly. It would be more, um, I would render everything on the nano, on this, on the screen, and then I would kind of take a screenshot of that and then render that out. I mean, I could find easier, I could find quicker ways to do the rendering as well. It's just that if I want to do something fancy, or even just drawing shapes, like Nano would do an amazing job of that. So I don't need to, you know. Yeah, yeah. I don't know, because Nano is great as a creative coding framework, but it's meant for, like, more live coding kind of stuff. Not live coding, but like creative coding kind of, though, because it's meant for creative coding. So I think it would also include functionality for this kind of thing where you could export whatever is being displayed on screen right now, or I could just get another. There might be some other Rust library um, that can sort of export the current frame that's being rendered. Yeah, now if I do try to do that, then uh, I feel like I would be able to do a much better job now, because previously I was planning on using Unity to do that. Now I would be using, well, Rust. The thing is, though, if we are talking about visualizing these data structures, yeah, you know what? I could create a sort of tool that helps visualize these data structures. I want to, dude, no, no, no. I want to, yeah, now I want to, now I actually want to try and set something like this up. I want to set something like this up. I want to see how well I'm able to do it. I could possibly use Rust's ND array in order to do that. Anyways, let's continue reading this. Where was I? What are we doing here? There's oh, yeah, operations, tensor operations, and then reshaping. Okay, element-wise multiplication, then matrix multiplication. Wait, can these two even be multiplied? Oh yeah, okay, they can be multiplied. They're square matrices. So in this case, um, m by p is equal to, or, well, there's m by p, and then there's p by q. So the columns in one are equal to the, or the number of columns in one are equal to the number of columns in, the number of rows in the second one. The columns of the first one, holy shit, the number of columns in the first matrix is equal to the number of rows in the second matrix. Why was that so hard to say? So yeah, in this case, the matrix multiplication is possible. Then we look into indexing, which is just like regular. Okay. Then we look into slicing, and then reshaping. Reshaping should be interesting. Hold on. Yeah, yeah, okay. Let's create. Yeah, we can do that. And yeah. Okay, tensor underscore a equals torch dot. Oh, okay. We're just defining tensors here. All right. Tensor, okay. 1, 2, then 3, 4. I'm hoping it doesn't require. I'm hoping it doesn't require the float thing and it just accepts the numbers, because otherwise I'll have to add a decimal after each of them. Okay, 5, 6, 7, 8. Oh, I could explicitly make it a float. Float 32, I think it was. Or was it float 16? No, float 32. Okay. I'm glad that I didn't erase the code from up here. Um, okay, dtype torch.float 32. Right. What else is there then? We just print them out. So we print out tensor A, then print out tensor B, then print out addition. I'm assuming this is element-wise addition and then element-wise multiplication as well. Yeah, let's do tensor A plus tensor B. Then we want to do multiplication. So element-wise multiplication and then matrix multiplication. What else are we trying to do? Okay, indexing and slicing. All right, so print tensor A 0, then print tensor A. Oh, so this is probably going to print the first entire row, right? And then this will print the second element of the first row, I think. Hold on. It's a two-dimensional array, right? So row 1 or row 0, which is the first row, and then element 1, which is the second column in row 1. Oh, so that's still then. No, um element at so and so. No, because like this is then being, I'm trying to, I'm kind of like confusing accessing values in a multidimensional array versus a jagged array. Yeah, I need to, for the sake of my just for the sake of experimentation here, because hold on. So that would be an array within, that would be multiple arrays within an array, right? That's how you'd be accessing a jagged array. But like, yeah, okay, what happens if I print it out like this? So 0 and then 1. But then that's assuming that 1 is a list. If 1 is not a list, then this is supposed to throw an error, right? Let's, no, it doesn't. We are able to access it in both ways. What am I missing here? There's something I'm having trouble like visualizing. Hold on. Because in a multidimensional array, a multidimensional array is not necessarily a jagged array. I wonder if PyTorch is abstracting away that detail. Yeah, yeah. You know what? Let me open up a separate instance of Gemini here real quick, because this is some. Or wait, no. I'm planning on exporting this conversation, right? So I can ask this. I can ask the question to Gemini. Uh, right. Let me go through reshaping the tensor. Yeah, let's go through the reshaping part and then look into. Oh, we might as well do the slicing thing. You know, I'm realizing I don't use slicing nearly enough. Like there have been situations where I've used it, but it just doesn't occur to me to use it, if that makes sense. That's not the first thing that comes to my mind. The first thing to come to my mind would be like some more convoluted way of accessing the data, which could have very easily been done using slicing. Okay, so let's see what this slicing method gives. This gives us, that's interesting. Back up, back up. How do I, wait, I forgot about this thing. Okay, yeah, anyways, how do I, how do I look into that? I think I'll just ask Gemini about that. What information did Gemini give? Accessing specific parts of a tensor, similar to Python lists or NumPy arrays. Oh, you know what? Okay, let's do something here. Um, okay, let's open up a Python thing here. A equals 1, 2, 3, 4. A, this, that. That gives an array. That gives an error. Because this is not multidimensional, what if I make it multidimensional and do this and that? List indices must be integers or slices, not tuple. Right, so I think the slicing syntax is something that's being implemented uh, within PyTorch. And I believe NumPy probably has something similar as well for being able to slice ND arrays. Though here, if I did, let's say 0 to 2, so 0 here gives us that. That is our, okay. Here is how I would be accessing it. So I'm guessing PyTorch abstracts away the difference between accessing like a multidimensional array versus a jagged array, because I'm guessing internally it represents the entire thing as a multidimensional array and not a jagged array. I do need to ask the question about this. Okay, so we have two questions now. What else was that? Reshaping. Yeah, let's take a look at reshaping. Reshaping was also interesting. Okay, reshaping. Original tensor equals um, torch dot arrange, not array, torch dot arrange. Oh, it's not arrange, it's a range. What does that do? It returns a 1D tensor of size so and so with values from the internal start and end taken with common difference step beginning from start. Returns a 1D tensor of size um, I'm having trouble reading this. Is that what? No, hold on. Let me see the docs. PyTorch torch dot a range. Okay, returns a 1D tensor of size step end minus start. There's a step end. Oh, oh, this is different. Okay, so it's end minus start divided by step with values from the interval start to end, taken with the common difference step beginning from start. Right. Maybe I don't need to focus too much on the definition of this. Right. So let's just print out original tensor and then print out original tensor dot shape. Then reshaped tensor equals original tensor dot view. Dot view is used for reshaping. Alternative is reshape. This returns a new tensor with the same data. Does reshape also do that? This returns a tensor with the same data and the number of elements. This method returns a view if shape is compatible with the current shape. See torch tensor. Oh, this might be a difference between returning a new tensor versus returning. No, even if it's returning a view, isn't that? Hold on. Tensor.view versus tensor.reshape. View and reshape are used to change the shape of a tensor, but they differ in how they handle memory and contiguity. That's a whole, I've never used that word. Okay, right. View requires contiguity. View can only be called on a contiguous tensor. A tensor is contiguous if its elements are stored in a contiguous block of memory and its strides match a C-style layout. It returns a view. View always returns a view of the original tensor, meaning it shares the same underlying data in memory. Changes to the view will affect, okay, it'll affect the original tensor. This makes it very efficient as no data is copied. It fails on non-contiguous tensors. Okay, then reshape handles contiguity and handles contiguity automatically. Uh, reshape is a more flexible. No, reshape is more flexible and can handle both contiguous and non-contiguous so and so. Returns a view or a copy. If a tensor um, is contiguous and the requested shape allows for a view, um, that is, a new shape can be achieved by simply reinterpreting the existing memory layout. Then reshape will return a view. Otherwise, if the tensor is non-contiguous or the new shape requires a different memory layout, then reshape will create a copy. Okay, for now we don't need to focus on that. Let's just do this. It says 3 by 3. So this turns a 1D array into a 2D array with 3 rows and 3 columns, right? So then if we print reshaped tensor and print reshaped tensor dot shape, then we'll get those values. So let's come here and print this out. Yeah, there it is. So that's our array, that's the shape, and then the thing gets reshaped, and that's the shape now. Right. What more was remaining? Yeah, that's about it. Oh, there's one more thing. PyTorch infers the second dimension. -1 can be used to infer one dimension. Oh, so it'll use whatever can fit. I'm guessing that's what it means. It'll use whatever can fit, which in this case I believe is also 3, right? Let's try that. Because like it's 9 elements, right? Let's think about how you could rearrange 9 elements. Though, okay, let's say I did this. This wouldn't be like a, yeah, I'm not sure how it would do this shape. Yeah, there's an error. Okay. Is invalid for input of size 9. Yep. Okay. All right. It infers what? It infers the second dimension. Right. What if we could we infer the first dimension as well? Let's try inferring the first dimension and then try running this. Yes. Okay. So it tries to fit it in whatever way it can. So let's say we made this 10. Okay. We could then do something like this. And we would get that shape. Or we could do, we can't do 4. We can do 5. And then we'll get this shape. Yep. Yep. Okay. Great. Awesome. Okay. Um, I'm done with, what am I doing here? Okay, I'm done with that. I do have some questions. Um, what was a question? Um, the question was relating to, oh, yeah. accessing, okay, help me understand how I'm able to access tensor underscore A using this and this. Um, and I get the same output. Isn't one accessing a multi-dimensional, no, isn't one a way of indexing a multi-dimensional array and the other a way of indexing a jagged array? Then next question, help me understand the the slicing method. I'm having trouble understanding exactly how tensor underscore A and this, and what was the exact thing that okay, 0. 0 is working. Okay, let's let's wait for the response. In the meantime, is there anything else that I missed? Let's actually let's scroll up. So we are currently looking at tensors. We just got done with tensor operations, the concept of a computation graph, and automatic differentiation. I don't think we're going to have to do anything ourselves. Um, yeah, I don't think we're going to have to do anything ourselves over here. The concept of, because the computation graph and the automatic differentiation, that it's a more advanced concept where it's kind of recording the operations that are happening on this on specific like tensors, and it's constructing an entire graph out of that so that it can kind of traverse that graph to like walk back. That's where the automatic differentiation comes in, or well, autograd. uh okay, we are still going. Oh yeah, I did ask questions, right? Yeah. So I'm guessing it's gonna respond to my questions, and then we're gonna move on to the next thing. For now, it's gonna be explaining this to me. Okay, right. Those are fantastic questions. It's crucial to understand these indexing and slicing mechanics. Let's break them down. Indexing. This was that. You are absolutely right in thinking, in your thinking. In many languages, this is for jagged arrays, arrays of arrays, where inner arrays can have different lengths, and that is for multidimensional arrays, like a grid or matrix and where every row has the same number of columns. Okay. PyTorch tensors are true multidimensional arrays. Every row in a 2D tensor must have the same length. Okay, all right. Every row in a 2D tensor must have the same length. Every row, okay, this is specifically 2D tensors. I need to see how um, how that's applied as the dimensionality increases. Like, what's the rule then in three-dimensional and four-dimensional and five-dimensional tensors? Okay, so why do both syntaxes work? The multidimensional one is recommended, apparently. This is the standard, most efficient way to index a multidimensional array in PyTorch and NumPy. You're providing a tuple of indices in a single operation. It directly accesses the memory location for the element with the first row index 0 and the second column index 1. Okay. Then the second method is it's called chained indexing. This works, but it's a two-step process. First, tensor, oh, okay, first so-and-so is executed. This operation selects and returns the entire first row of tensor A, which is that. Then the second index is applied to that newly returned tensor. It selects the element at so-and-so. While both give you the same result for reading data, the multidimensional syntax is generally preferred because it's a single atomic operation and is more explicit about operating on a 2D grid. Okay, then slicing. This is the standard way to slice a multidimensional array. This is the standard way to slice multidimensional arrays. Let's break down the syntax, rows, columns. The colon is a special character that means select all along this axis. So when you write so-and-so, that's the first position for rows. Get all the rows. And then this is the second position. So get the element at index 0 from the columns. Oh, so this is a way to get the entire first column or second column or whatever. Let's test that out. Let's print, what is it? Tensor A. Did we change tensor A? I don't think we did. Okay, tensor A, this, and then that. So now it makes sense why it returned, I believe 1 and 3. Actually, no, not 1 and 3. What value did it? It returned some value. I don't remember what. So this returns 1 and 2. This is returning 1 and 2. Oh, yeah, I made a mistake here. Now it makes sense. Yeah, now it makes sense. Let's print out tensor A again. Yeah, there it is. Okay, so slicing can be useful for this purpose. Yeah, like I mentioned earlier, slicing is one of those things that I should be using it more often, but it just doesn't occur to me to use it until much later, that is. So this is great. This is a way to access columns in a multidimensional array. Though, hold on. What if I tried to slice No, would that even work? I don't think that would work how I'm thinking it's gonna work, because if I try to slice row, let's say one, and I do this, it's just gonna return the entire row, isn't it? Yeah, it's just returning the entire row. Yeah, okay, I had like a different idea, but like, yeah, the point of slicing there, well, okay, it can still be used. It can still be used in even in that situation. If your row is that big, then yeah, it can be used. And I'm guessing this is also a thing. So it's just returning the entire tensor then. Okay, cool. These are fundamental concepts, so it's great that you're digging in to understand them. Now let's move on to the final and perhaps most magical topic of chapter 1, automatic differentiation with AutoGrad. This is the engine that makes neural networks learn. Shall we proceed? Yes, please. Now let's type. Yes, please. Okay. Right. Excellent. The next concept is what makes PyTorch so powerful for deep learning. The concept of a computational graph and autograd. Remember when we said a neural network learns by adjusting its internal parameters to make better predictions? This adjustment process is a core concept called backpropagation. To do this, the network needs to figure out how a small change in each parameter affects the final output error or the loss. This is a calculus problem. We need to find the gradient or derivative of the loss function with respect to each of the network's parameters. Doing this manually for a massive network would be impossible. This is where PyTorch's AutoGrad comes in. PyTorch automatically builds a computation graph behind the scenes. Every time you perform an operation on tensors, PyTorch adds it to a graph. When we are ready to calculate the gradients, PyTorch uses this graph to work backward from the final output and automatically compute the gradient for every parameter. Okay, how to use it. Requires grad and dot backward. To tell PyTorch that we wanted to calculate gradients for a particular tensor, we set its requires grad property to true when creating it. These are typically the weights of our network, the parameters we want to learn. No, wait, hold on. To tell PyTorch to calculate and so for a particular. Oh, the tensor. Yeah, yeah. True, true. The tensors are they would be the weights. Let's see it in action. Update your chapter 1 with this final piece of code. AutoGrad example. Oh, good. Okay, they have something to demonstrate this. Yeah, I've always found this bit interesting because I've never gotten the chance to dive into the math of this specific thing, specifically um, calculating the gradients with respect to each calculating the loss of the gradient with respect to the current weights, and then um, using I think it's called the chain rule to sort of walk back from your final output all the way to the beginning. Like what exactly is happening in that process is what I need to understand, and what I need to get like a conceptual understanding of it, a higher level understanding of it, because I don't know that level of calculus, and I don't want to dive deep into that level of calculus either, because that's going to end up taking more time. Besides, I don't need to do that because AutoGrad exists. My intent with learning how it works is primarily curiosity. I just want to learn how it's happening, because like in the end, the result there is that based on this gradient, we pass this gradient to an optimizer, which PyTorch has a couple of optimizers implemented. We pass this gradient to an optimizer, and then the optimizer updates the weights based on certain parameters, and then you run the entire network again. Okay, all right. Let's read the code. AutoGrad example. So this is our tensor, requires grad, create a tensor X. We want to compute gradients with respect to it. Okay, I'm also going to ask one more question just for the sake of, curiosity there. But yeah, I'll ask that question later on. Okay. Uh, we want to compute the gradients. Okay, create another tensor. Think of this as the weight. Okay, y equals w multiplied by x. Okay, weight multiplied by the input. And then the weight is going to be, wait, what else? Let's do one more operation. Y plus 2. Oh, so this is a basic linear, uh, well, I mean, I don't know to what extent this would be called a linear operation if it's just one value, but like, yeah, it's that concept. It's input multiplied by weight plus bias. Z is our bias here. Z is not the bias. Z is the final output. 2 is the bias. Z is the final output that you get from this entire operation. So the operation here is W multiplied by X plus 2. Though it's being divided into multiple steps, I'm guessing so that we can see the gradients. Actually, no, Y's gradient is not being calculated at all. Okay, now for the magic. Where was I? Yeah, now for the magic. We want to find the gradients. Okay, okay, and that PyTorch does this with the backward call. This call must be on a scalar output. All right, so let's do that. Okay, x equals torch.tensor. Oh, it's just like a one value kind of thing. Okay, true, then w equals torch.tensor. 4 requires grad, true. Then y equals w multiplied by a. Did I say A? No, W multiplied by X. Then Z equals, oh, you know what we could do here? Yeah, we need to print out a couple of things. So here we can do X, wait, this would make it easier. Yeah, let's just print a long line, and then that'll be much easier. Okay, then X and print W. Might as well print Y as well. Then Z equals Y plus 2, and then we print Z. Then Z dot backward. And then we print out the gradient for, yeah, what are we doing down here? Oh, okay, so when we do Z dot backward, uh, all the calculations are done, and then X and W are automatically updated because they are part of that calculation. And I'm guessing that's where the graph comes in. It builds all those connections. So let's do this. Okay, gradient so and so is X dot grad. Okay, gradient. This is W dot grad. Okay, let's run this. Okay, so these are our tensors. We did 3 multiplied by 4, which gives us 12. And then 12 plus 2 is 14. So that's our Z. And then when we calculate the gradient, it's 4 and 3. Okay, so I have some follow-up questions when it comes to like gradients and stuff. I am going to try and get like a conceptual understanding through this without diving too deep into the math of it, because I know the calculus behind this is fairly complicated. So I don't want to end up spending too much time on this. I want to be able to move on from this quickly. So I'm going to ask the question, but before that, this is so we are pretty much done with chapter 1. Then we'll be moving to chapter 2, which is where we actually build the neural network. Okay. All right. Now, hold on. Okay. Just a second. Okay, you know what? I have a couple of choices here. Actually, okay. I want to see if this person's thing is open. Uh, okay. All right. So we're gonna go to this person. Their name is Louise McJagger. That's interesting. We're gonna go hang out in this person's stream. Yeah, that's gonna be it for today's stream. Guys, thanks a lot for hanging out. Deebs, thank you for the follow and thanks for hanging out. Um, anyone else who might have been lurking in the chat, thanks for hanging out. We are once again we are still on a streak. We've got a pretty good streak going, and I'm pretty excited about it. Like I haven't missed a streaming day in a good 2 weeks, I think, and I'm excited about that. I'm happy. I hope it's still. I hope it keeps going. And I'm excited to get back into deep learning now through Gemini. But yeah, dude, that's going to be it for today's stream. I hope you guys have a nice day, and I'll see you all next time. Peace.